So thank you, Mark. Then we move on to the next paper, which is José Manuel. I think hopefully you are able to put the presentation up. I think we are now moving to an area where I think basically we've had these machine learning techniques, I think theoretically for some time, but I think with the emergence of more raw data power and also the availability of data, I think the practical implication of credit scoring model is something that is kind of developing, and I suppose Manuel will bring us through their presentation on this. Thank you very much. And are you ready, José Manuel? Thank you. I think we cannot hear you.
So let me know when you can see my slides.
We can see them now, but perhaps maximize the screen otherwise.
Okay, can you see it now?
Perfect. Thank you.
Excellent. So, well, yes, thank you for being here. My name is José, and today I will talk to you about this paper called Understanding the Performance of Machine Learning Models to Predict Credit Default. This research has been done by Andrés Alonso from Banco de España and by myself from Banco of España as well. So let me start with a bit of motivation. So we know that from recent surveys that institutions are increasingly using machine learning for different things, for calculating regulatory capital, for calculating provisions, for credit scoring, etc. And if we look at the literature review, we can see that machine learning models, the complex ones, usually yield a better predictive performance than the traditional statistical models like Lasso or Logit. The problem is that from a supervisor point of view, these machine learning models may bring new challenges like interpretability, biases, or dependency on third-party providers. Therefore, before entering the risk analysis, we should understand better which are the real economic gains from these machine learning models. Since from the supervisor point of view, these machine learning models are going to be a challenge to supervise, we need to understand which are the economic gains that institutions might get when they use machine learning. This is the motivation that leads us to our research question. The research question in this paper is that we would like to study the performance of several machine learning models for credit default prediction. And we would like to understand as well the potential economic impact for the institutions. In order to do this, we will use a unique and anonymized database from a Spanish major bank. And we will compare the statistical performance of 6 models: Logit, Lasso, Tree, Random Forest, XGBoost, and Deep Neural Network. I will explain later on what do I mean by statistical performance. And then once we see the statistical performance, we will translate this statistical performance into economic impact by estimating the savings in regulatory capital under an IRB approach. So what does it mean? It means that we will take Lasso, a traditional model, we'll do predictions about default, we will use those predictions to compute regulatory capital, and we will do the same process but with a machine learning model, XGBoost in this case, and we will see the differences in regulatory capital. And the differences, we see that the differences are from 12 to 70%. So using machine learning models can yield savings of from 12 to 70% in regulatory capital. And we believe this might be a lower bound of potential benefits. So let's go to the data set first. So the data set, it's an anonymized database of consumer credit from Banco Santander. And this data set has more than 75,000 credit operations, so more than 75,000 loans that have been classified into 2 groups, depending on if the loans were defaulted or not. And additionally, for each loan, we have up to 370 features. So we know 370 risk factors for each loan, but we don't know the labels or the description behind these features. 4% of the loans in the data set resulted in default, but the data has no temporal dimension. So we don't know if the data, so we don't know when the loan was granted, and if it resulted in default, we don't know when it happened. So this is the data set. And now I will tell you what do I mean by predictive performance. So to assess the predictive performance of the 6 machine learning models, we will focus on 2 things, 2 tasks, classification and calibration. So why these 2 things? Because these 2 tasks are explicitly mentioned in the validation process of a rating system under IRB approach. So basically, under the current regulation and the current Basel guidelines, the banks can estimate their own probability of default for computing regulatory capital, but these estimations must be good at classification and good at calibration. That's why we use these 2 measures to understand the predictive performance. So what is classification? Classification means discriminating between which loans are going to be default or not. and the suggested metric by the regulation is the area under the curve. And what is calibration? Calibration refers to how good is the probability of default, how good is the estimation itself. And the suggested metrics by the regulation are the Breer's score and the reliability curves. Okay, so let's see how good are the models at classifying and at calibrating. So first, classification. So we're going to see the classification power of the 6 models under different circumstances. We want to see which is the classification power when we have different sample sizes from 1,000 loans to 65,000 loans. And we're going to see what happens to the classification power when we change the number of features available. So for example, let's focus on the left-hand side graph. And here on the left-hand side, we can see 6 lines, one for each model. And we see on the horizontal axis, we have the number of loans available. So we run many simulations for 10,000 loans, 20,000 loans, up to 65,000 loans. And on the vertical axis, we measure the area under the curve. So the higher the area under the curve, the more classification power. We can see that for all the models, the more loans we have in the data set, the higher the area under the curve. But for Logit and Lasso, that are the yellow and the blue line, once we reach 15,000 loans, the area under the curve doesn't increase as much. So above 15,000 models, the rest of the machine learning models, the 4 machine learning models, have better classification power than Logit and Lasso. The ones that have the best classification power are Random Forest and XGBoost, that are the purple and the brown line, and they are 4 or 5% higher than Logit and Lasso. Neural networks, despite being the most complex models, are not the one that classify the best. And so the thing that is interesting here is not only that machine learning models can adapt to hundreds of thousands of data or millions of data. As soon as we have more than 10,000 loans, complex machine learning models can classify better than Logit and Lasso. And on the right-hand side, we have a similar, we perform a similar exercise. We run simulations in which we change the number of features available. So here we have all the data available, the 75,000 loans, but we change in each simulation the number of features from 100 features to 375 features. And again, on the vertical axis, we have the area under the curve. So we see that for all the models, for the 6 lines, we see that the area under the curve gets better as soon as we put more features into the model. But again, we see that Logit and Lasso, that are the yellow and the blue line, are the ones that perform the worst and are always around 4-3% below what Random Forest and XGBoost can achieve, that are the purple and the brown lines. And again, Random Forest and XGBoost are the best performing models. And again, we see that it's not only that machine learning models can adapt to more features. It's not that machine learning models can adapt to hundreds of thousands of features. As soon as we have more than 100 features, machine learning models already can classify better than Logit and Lasso, that are the standard traditional statistical models. So this is classification. What about calibration? Calibration refers to how good is the probability of default itself. So according to the guidelines of the regulators, we should use Breer's score, but we don't have time to go into detail with the Breer's score. Let me tell you that, again, XGBoost and Random Forest have a better Breer's score than Logit and Lasso. And let's go to the reliability curve. So here in this slide, we have a reliability curve. What is this? In this graph, what we do is we run hundreds of simulations and we take all the predictions and we group the predictions by probability of default. So here we have on the horizontal axis, the average of the probability of default. And on the vertical axis, we have the fraction of default of that group of loans. So for example, if you go to, I don't know if you can see my arrow here, if you can see the, oops, sorry. So for example, if we go, a perfect calibration will mean that if we are on the horizontal axis on the 20%, that will mean that that group of loans has an average of probability of default of 20%. And then a perfect calibration, if we are in the 45-degree line, that will mean that we have a fraction of default of 20%. So that's perfect calibration. But we see that the models are not on the 45-degree line. They are away from it. And the ones that have the worst calibration are, again, Logit and Lasso, that are the blue line and the yellow line. For example, if we see on the horizontal axis around 10%, Logit and Lasso put a group of loans there, and for Logit and Lasso, those loans have a probability of default of 10%, but the fraction of default of those loans was actually 15%. So Logit and Lasso are underestimating the probability of default. But then if we go to the horizontal axis on 25% probability of default, Logit and Lasso, yellow and blue line, they are putting loans, and Logit and Lasso consider those loans have a probability of default of 25%, but the fraction of default of 25%, but the fraction of default is actually 15%, so they are overestimating. So again, we see that in this task, in calibration, Logit and Lasso are the ones that are performing the worst, and XGBoost and Random Forest that are the purple and the brown line are the ones that are closer to the 45-degree line. Okay, so this is, I know I have been very fast, but we see the statistical performance. Machine learning models can calibrate and can classify better than logical lasso. Okay, so which is the economic impact of this? We are going to compute economic impact by computing the savings in terms of regulatory capital under an IRB approach. So we are going to compute the regulatory capital using Lasso, that is a traditional model, versus XGBoost, that is the best performing machine learning model. So if we go so let me just tell you what is the capital requirement. So what is the capital requirement for a group of loans? So on the bottom we can see the formula for capital requirement. I don't have time to go into detail. Let me just tell you that the capital requirement for a group of loans depends on the probability of default of that group of loans. And that relationship is concave. The higher is the probability of default of the loans, the higher is the capital requirement, but each time less and less. And this will have consequences. Okay, so let's compute the capital requirement for Lasso and XGBoost, a traditional model and a new machine learning model. So first, we take the original data, 75,000 observations, we take 60,000 to train, 15,000 to make predictions. So we have 15,000 predictions about loans, and we order those predictions into 50 buckets, and depending on the probability of default. So for example, on the left-hand side, we have the 50 buckets for Lasso. Each bucket has 300 loans, and we order the buckets depending on the probability of default of the loans. So on the left-hand side, Lasso, for example, we can see the 50 buckets, and we can see on the vertical axis the probability of default and the observed default of each bucket. We can see that, for example, that in bucket 40, Lasso considers that the average of the probability of default for those loans is 7%, but the actual fraction of default was only 2%. So Lasso is overestimating. And then if we go to bucket 45 in Lasso on the left-hand side, we see that it's the other way around. Lasso is underestimating the fraction of default. While if we go on the right-hand side to the XGBoost, we see the 50 buckets for XGBoost, and we see that it's much better calibrated. So in each bucket, the difference between the probability of default and the observed default is smaller. Okay, but these are 50 buckets. A regulator will never allow to have a calibration of 50 buckets. They will ask for 10 buckets, and not only 10 buckets, they will ask for two criteria, that the buckets should be heterogeneous and the buckets should be homogeneous. Heterogeneous among them and homogeneous within them. It means that the buckets should be similar. The loans in a bucket should be similar. So we take the 50 buckets from before and we build a new calibration of 10 buckets. This is the picture. On the top we have the picture for Lasso, and on the bottom we have the picture for XGBoost. And you can see we have 10 buckets still. For Lasso, we have big differences between the probability of default and the fraction of default. In bucket 6, there is a big difference. Lasso is underestimating the fraction of default. But there are also differences for XGBoost. The supervisor will never accept this because we don't accomplish the two criteria of heterogeneity within between buckets and homogeneity within buckets. So this will be the final classification. This classification for Lasso on the left-hand side will have 6 buckets, and for XGBoost will have 8 buckets. This calibration will actually comply with the criteria from the supervisor, and this could be accepted. Now we have in each bucket a small difference between the probability of default and the observed default. But why is XGBoost? Why can we have more buckets for XGBoost than for Lasso? So let me come back to the 50 bucket slide. Again, because for Lasso is unable to differentiate as good as XGBoost. XGBoost delivers a much granular classification of probability of defaults. For example, look at on the left-hand side at bucket 40. Lasso is unable to differentiate between bucket 37 and bucket 42. But those bucket 37 is very different from bucket 42 because bucket 37 has a very low fraction of default, and while bucket 42 has much higher. So Lasso has like flat areas on the left-hand side, flat areas among which we cannot differentiate correctly between loans. That has as a consequence that with Lasso we can build less buckets than with XGBoost. With XGBoost we can differentiate better. Okay, and now we go to the last slide of the presentation. What has all this to do with the regulatory capital? On the left-hand side, we put the 6 buckets of Lasso and the 8 buckets of XGBoost together in the same picture. And we see that the probability of default, and we see the probability of default for those buckets. We see that the probability of default of bucket 5 and 6 of Lasso is higher than XGBoost, and XGBoost has bucket 7 and 8 because Lasso don't have those buckets. And on the right-hand side, we have the regulatory capital of each bucket. And we see that the regulatory capital for bucket 1 is higher for Lasso, the regulatory capital for bucket 6 is much higher for Lasso. And if we take the average of this regulatory capital, we will see that actually regulatory capital for XGBoost is between 12 and 70% lower. And this difference is because there are different formulas for regulatory capital. But in summary, if we take the weighted average of the regulatory capital of the loans in each bucket, for XGBoost we can have a lower amount of regulatory capital. That's because for XGBoost most of the loans are between bucket 1 and 5, and XGBoost and for Lasso many loans are in bucket 5 and 6, and the buckets that have the most number of regulatory capital. So again, let me conclude because I run out of time. In this paper, we have studied the performance of several machine learning models. I have shown you that the statistical performance of complex machine learning models is better than Logit and Lasso in terms of classification and calibration. And in this paper, we have tried to translate that statistical performance into economic impact. The fact that XGBoost is able to classify and calibrate better allows XGBoost to deliver a more granular probability of default, and allows XGBoost to has a different distribution of buckets and have a 17% lower regulatory capital. So this is an important figure, and since it's an important figure, this led us to suggest that more research is needed to understand now the cost. Now that we understand the benefit, and it seems to be an important benefit, we have to understand now the cost. Yes, I'm finished.
Thank you very much, José Manuel. As a discussant, we have Klaus Duellmann from the ECB, which I assume has I know has a long history behind the IRB, probably longer than he cares to admit. So I'm looking very much forward to seeing your comments, Klaus.
Yeah, thanks a lot, Lars, and thanks a lot to all the organizers for inviting me to this conference here. I try to share content. Here it comes. So first of all, let me say that I very much enjoyed reading the paper. I'm just putting it on full screen, and my comments are not fundamental, but touching upon a couple of things where I think the authors could improve a little bit, and have also some more fundamental questions on the way how two aspects are sold. So I would first of all go to the contribution and the overview. Then I will look at the comments on how the supervisory costs of machine learning models are assessed. Then I have a comment on the calibration measure, the BRIA score, and then I would like to make a few points where I would see room for the authors to make their case more convincing. Now, the contribution of the paper is to explore the performance of several machine learning models for credit default protection, and also to estimate the respective regulatory capital relief, which is, I would say, substantial. And the latter thing is really an aspect that is new, that we do not find in other previous papers. Performance analysis is based on uniform and I would say pretty rich data set of a bank, and the questions are highly relevant from a policy perspective in light of ongoing discussions on the use of machine learning for estimating regulatory variables. So particularly relevant in this context is a potential trade-off that also the authors are mentioning in the beginning of the paper between, on the one hand, a potentially higher predictive performance if you go to these more advanced and technologically newer methods, versus less transparency on the underlying economic mechanics that render the supervisory evaluation more difficult. Now in the paper they follow a three-step approach in their performance evaluation. They start with the statistical performance. They look at the classification with the area under the curve and the RC measure. Then they go to calibration. Here they use the BRIA score. They have also another approach, but I will focus here my comments on the BRIA score. And this is something new that you don't find in previous papers, they also look at the economic impact. And then they more specifically explore here the impact on the capital requirements on the risk-weighted assets. The portfolio was very well explained by the authors, so I will be here short. I just would like to mention that I found this pretty impressive to have 370 risk factors for every credit operation. This is in this sense a very rich data set. It also has some, let's say, unusual drawbacks. For instance, it doesn't have a time dimension. And that's also the reason why they don't use any macroeconomic variables, and I'm coming to this also a little bit later. Now, my first comments are on the selling point. You want to contribute to the supervisory costs of machine learning models issue. And you mentioned this trade-off between better predictive performance on the one hand and higher supervisory costs of these models in your motivation. What you are doing more precisely, if I understand correctly, is you see your economic impact analysis, to which I will come back later, as the main contribution. And this is, of course, very interesting. But my question is the RWA reduction really part of the supervisory costs, or is it not rather a justified consequence of a simply better performance in measuring risks? And in this sense, it's not a cost, it's just a logical consequence. So if the supervisory costs are instead rather driven by what you also mentioned, the interpretability and stability of the predictions, by the governance of models, then if you want to dive into this trade-off question, it might make sense to look into these issues and not so much in the capital reduction. If you look into the RWA, then one question is, why don't you look at another component that's also important for the solvency ratio, which is the EL? And then I would see value in also speaking a bit more about the intuition behind the RWAs being lower for the better performing approaches. My understanding for paper was it's basically driven by that you have, let's say, more buckets, so you can do a finer calibration. But of course, also the PDs are different, and ex ante, it can also be that with a better approach, you could also have, let's say, higher PDs. Yeah, so maybe it would be useful to discuss this a little bit more, why you get to this result, or is it just only driven by the number of buckets? Look, then I come to a second comment, which is on the calibration measure. Here you use the Brier score. And my question is it really a clear-cut calibration-only measure? The Brier score, in essence, is, as we know, a sample estimator of the mean square difference of the default indicator variables and the default frequency estimates. And in this sense, it can be also interpreted as the, let's say, the residual sum of squares from a nonlinear regression of the default indicators on the rating. So minimizing the Brier score is equivalent to maximizing the variance of the default frequency estimate. But this is something that we also see that the ROC measure does. And the ROC measure is definitely a measure for discrimination and not calibration. So the Brier score is a measure of discriminatory power 2. So in this sense, if you use it, you are not fully sure if you measure only the calibration part. And my question is, why not use alternative measures like the chi-squared or Holzmeier-Lemenshoff test? Also because this is suggested, as well as this point on the Brier score, in an old paper by the research task force of the Basel Committee on the validation of weighting systems, which is also cited by the authors. So I was a bit surprised why this test is not used, which is also used in practice, as far as I know. Now, my third comments are on maybe different from the first two, because they don't necessarily need to any new calibration or changes or computations. It's more about how to make the case convincingly. So it's more about the presentation part. The viability of a performance analysis depends on that the models in the horse race are representative for their respective class. In particular, if a model performs inferior, we must be sure that it's really representative and not just a bad model out of this class. This is important to convince the reader, and for this reason I would see value to have more information on the individual algorithms and also on the robustness of the models on the different algorithms. The paper is really very short here, and this could make the reader a little bit more confident. It could also be useful to use statistical tests on equal or superior predictive performance. And related to this, I mentioned before the lack of macroeconomic variables, for which we have a good reason. I guess it's a sample limitation, but I wonder if this maybe poses a systematic disadvantage to the regression-based models, the classic linear models, logit models. These regression models have been pretty successful in the past because they use these macroeconomic variables, and this was all in this linear framework, right? So the question is, if you are now looking for maybe variables which miss an important part of the explanatory power, and for this, which might be maybe even more nonlinear, maybe the more sophisticated approaches are better, but it's maybe really driven by the selection of explanatory variables. So this discusses might be useful. Also to discuss a bit more the interpretability of the results for the more advanced algorithms. I see I'm just at the end of my time, so I will skip or I will go very quickly only to the last 3 slides. So more information on the algorithms. This can be how is the logit model chosen? Is it the result of a best subset regression? Could also modeling averaging approaches like the Bayesian model averaging increase the performance, and then maybe you get a different value before drawing conclusions about logit models in general. Then what I mean by more information on the robustness of models, here you could talk a little bit more about the cross-validation. As I understood from the paper, there is this distinction between the 80 and 20%, but it's only a very crude way to do cross-validation. I would assume that the approaches also do maybe their own bootstrap or H-fold, 10-fold, whatever it is. So here, this could be useful. Also, statistical tests on equal or superior probability of performance. I've mentioned a few examples, something you might want to look into. The lack of the macroeconomic variables I already explained, and the interpretability of the results from the more advanced algorithms. I think this is really this is important. Also touches on the fundamental question on the trade-off I started with. There is a balance between performance, model stability, interpretability of the models, and this could be an avenue to go a little bit deeper into. Well, the summary basically summarizes what I said. So in the interest of time, I will stop here. Just mention the last bullet where it says, I recommend reading this paper. It is well written. It opens a strand of literature that is becoming more and more important with the technological advances that we see. With these improvements, I think it can be even more important going forward. Thanks a lot.
Thank you very much, Klaus. I would suggest that we also take the questions directly. I think we have 4 questions, and I think this is about what we can manage to do right now. But I think the points raised by Klaus are very relevant in terms of the robustness of the analysis, because I think if it is sensitivity which is improved, then it's fine. But I think the questions are also touching on this, and I think the first is from Federico, which is about the introduction of so-called regulatory sandboxing, which is something that I understand is approved in Spain, but I think it's something that we are seeing in many European jurisdictions, whether that will encourage the further use of machine learning for credit scoring. The other aspect is probably one which will become increasingly important, namely privacy, ethical and legal issues in the use of data. So the more detailed information, what are the challenges that you see on this? Perhaps if you look at the data, is there variables that you would have identified can be problematic in this regard? And I think we have a very long question from Samuel also, which is going into very different kind of dimensions, but I think what are the challenges that bank supervisors have in terms of approving these models when it comes to machine learning versus other technologies? Are there elements that need to be improved in this regard? And I think is the analysis specific to consumer loans, or do you see possibility to expand to other data sources or exposure classes? Then I think the last question is from Dominique, namely on the robustness of the models. I think Klaus is presentation has some of the same elements. I think also here, how robust are the results? Because I think many of the things that we're seeing in the approval process is that supervisors also put in margin of conservatism depending on this. So understanding of the data quality issues and how this has been taken into account will be very important, because I think the true results will not be the model, but it will be also the subject to the supervisory approval, where there will, all of these issues will need to kind of be considered. But José Manuel, if you can try and summarize this in 3-4 minutes, then it would be perfect.
Yeah. So first of all, thank you very much, Klaus, for the discussion. You raised many questions. I cannot answer now all of them, but I will ask you for the slides, because many of the points were very good. So let's go from last to first. And so the question of Dominic about the robustness, that also Klaus raised some questions. So you're completely right. We will put more effort into that section of the paper explaining the cross validation and all the robustness that we have done, and we will perform some. So for example, we have performed H-fold cross validation. We have performed bootstrap, but we haven't. That section of the paper is weak, and we will improve it. So some of the robustness that we have made, for example, we have only 4% of defaults. So we have done oversampling and undersampling. So in order to see if the results are robust to that, because to the number of defaults, and we see that the results don't change very much. But definitely in the final version of the paper, we will provide more data about the robustness. And about the data quality, the data was given to us. We are very grateful to Banco Santander. As Klaus said, there are many features, and it's an extremely rich data. So we were lucky to have such a data set with such a quality. About the challenge from the supervisors, and also one of the questions that Klaus raised is what about the interpretability of the machine learning models? This is probably the biggest challenge with respect to logit and lasso. Logit, at the end of the day, it's very easy to interpret. You see the coefficients, and you have an idea of the general effect, and then you can compute the marginal effects just putting the features with the coefficient. And so this is the biggest challenge, especially in credit scoring, because in credit scoring, you have to, by GDPR, you have to give an answer of why you have deny or not alone, and you have to be able to explain why the machine learning method is giving that prediction or not. So that's the main challenge. We have to be 100% sure of why this machine learning model is giving that prediction. So we consider that the biggest challenge, and we haven't done anything in this paper about that, but Andres and I, we are already working on an extension of probably another paper will focus only on these interpretability issues. It's not true that machine learning models are not interpretable. There are techniques, there is the shape values, there are the feature importance, and we will, in this extension or new paper, we'll focus on this, and we believe it's the biggest challenge. And this question is similar. The question by Kim is very similar in the sense that the ethical and legal issues of machine learning is that we have to be able to explain to the customer why are we giving or not the credit, and in order to that we have to be able to understand and interpret the models as we are doing right now with Lasso or with a tree. And regarding the question of Federico, I hope that the sandbox will help, because it's our feeling that now there are many people talking about that machine learning models are a black box, but if we use it, thanks to the sandbox, we get more used to them, and we apply the already existing interpretability techniques to these machine learning models. We hope to make regulators also more familiar with the machine learning techniques and try to see if we can interpret them as good as we are already interpreting logic. And I would like to say that one of the questions about that Klaus raised, that the macro ones, we don't have macroeconomic variables, and it will be very interesting, one of the questions, to see up to which point this lack of information will be good or bad for when we compare logic and machine learning models. And about the Breer score, definitely the Breer score is a weak measure. It's just a mean square error, and we use that measure because it was our understanding that according to IRB it was suggested to use the Breer score. But we will use the technique that Klaus suggested. And I don't know if I have much time, or we are already out.
I think we are already more or less out, to be honest.
But thank you very much, Klaus, for the discussion and for your interest.
You're welcome. I will send you the slides.
Thank you.
Thank you very much. So.